I'm Usama, delighted to be here to share the work I did with my advisor, Benson, on improving CDN web performance. So digital services holds a key value in our life. We use them for business, for education, for entertainment, and for holding conferences. So due to their core key value, there's an incentive to improve performance. Research suggests that better performance leads to better user engagement, higher revenues, and better productivity. To improve performance, digital services typically use the caching and networking infrastructure provided by CDNs. Now, the CDN, a server at the edge of CDN interacts with the end user through its networking stack. Over the past many decades, the research community has done a marvelous job in improving the efficiency of these interactions. So today, we have multiple configuration options and protocols for each of the layer 4, that is transport, or layer 7, that is application. And all of these protocols and configuration options available have an impact on performance. Since digital services want good performance, it's the operator's job to select the right configuration that maximizes the performance. And these configurations are then used for the entire user base. Now, while all this sounds fine and dandy, there are two problems with this picture. First is, are the users really homogeneous? And the second is, if you're using the same set of configuration for the entire user base, is this approach really optimal? So in practice, the connections from users are not homogeneous due to a diversity of networks and devices. As performance of protocols can be sensitive to these features, it's a challenge for operator to select the right configuration that works optimally. For example, different network paths may have different latency, loss, and bottleneck bandwidth properties, and different congestion control model all of these aspects. So it's not quite clear what congestion control works the best for a given path. Similarly, a number of different device types are used to access web. And as device capability play a key role in performance, it's not quite clear that what configurations work best across the device spectrum. And third, while one might think that the newer protocols are always better, that's not always the case. For example, the research work shows that if your website has a lot of small objects, your network has higher latency and loss, then HTTP 1.1 actually works better than its successors. So this observation is actually broadly applied to a lot of configurations for the L4 and L7 layer. And the key takeaway is that one set of protocol configuration is not always optimal for diverse connections. So in this paper, we try to answer this question that how can we improve performance for diverse connection by dynamically reconfiguring the HTTP and TCP configuration. But before we move on to the system, let's take an overview of traditional approaches. So there are three approaches that are commonly used. In the simplest case, operators just simply keep the configuration that are set by default in kernel and server applications. In the second approach, operators run large-scale testing like A/B testing to test out different configurations and try to manually analyze the result to find what works the best. These configurations are then either homogeneously applied to all the users or selectively applied to workloads like video or web. In the third case, people build data-driven systems to dynamically tune configuration. In literature, we see examples for these systems for TCP congestion control, TCP initial congestion window, and for cloud configuration. Typically, algorithms like Bayesian optimization are used to quickly find a good configuration, which is then later exploited for other workloads or connections. So in order to test the efficacy of traditional approaches, we did a large-scale study where we emulated different network traces in a test bed and tested every single possible combination of configurations. Based on this brute force, we developed an oracle that has complete knowledge of configuration performance and can always select the best configuration. So the figure here shows page load time improvement on x-axis versus the default configuration and a CDF across page loads for diverse networks on the y-axis. We see that while the hand-tuned configuration do perform better than the default one at median, the performance improvement is capped at around 20% at tail because they use static configuration for diverse connections. The orange line here emulates a system that uses Oracle to dynamically tune TCP congestion control. And we see significant benefit with up to 50% improvement at tail. The green line here emulates a system that uses Bayesian optimization to tune the complete set of configurations. However, we did notice some suboptimality with convergence of Bayesian optimization, and that's why the results are not that stellar. Finally, we see Oracle here, and we see much better result than others. So we make 3 observations here. The first is there are significant benefits to tuning the configuration, as the improvement can be as much as 70% at tail. Second, the significant gap between the red and the orange line indicates the benefits of tuning cross-layer configuration instead of tuning just a single configuration like congestion control. And third, the significant gap between the red and the green line shows that the traditional approaches or algorithms like Bayesian optimization are suboptimal, so we need better algorithms. While Oracle has tons of benefits, it has one problem, that it's impractical because no one can know what the entire configuration space performance would look like. So our system called Configurator optimizes web performance by systematically reconfiguring TCP and HTTP layer configurations. So taking into input features like website properties, network condition, and device, it learns optimal or near optimal configuration in a very principled manner and reconfigures connection on a fine granularity to improve performance. The design of such a system faces a number of challenges when we are talking about CDN or internet scale. So the first is there's a QoE cost associated because if you test a bad configuration, then you are actually sacrificing some sort of revenue. Second, an automated learning technique would require building performance models for different configurations. But the CDN edge actually serves diverse last miles, diverse devices, and different websites. So there's a high dimensional nature to this problem, and it presents a challenge when we are building performance models. Third, network is dynamic, and network conditions change over time, over course of minutes. So the learning technique would be required to react to network changes and reevaluate how that impacts performance. Fourth, there's an inherent noise in internet measurements, and the learning technique would be required to tackle that noise. And fifth, there are system challenges regarding tuning configuration on a per connection basis in a low overhead manner. So basically, we see 2 sets of challenges. Some are algorithmic and some are system design challenges here. Now, the answer to many of these challenges rest heavily on what granularity we want. So we want fine-tuning granularity so that the yellow user gets its own optimal configuration, and similarly green and orange get their own. But the CDN edge does not serve just 3 connections. It's millions and billions of collections. And if we are trying to find the optimal configuration for each connection individually, it's a very challenging task and it's impractical. One option is to group the connection based on things like AS prefixes or edge locations. While this does help with amortizing the QoE cost, because like we can spread out the search to different connection in the same group, it does not address the fine-grained diversity and high dimensionality that may still reside within the AS or the prefix. So our insight here is that groups of connection with similar properties behave similarly. And based on this intuition, we designed a network classes, which is groups of connection with similar properties. And it helps us in addressing many of the challenges. First, it amortizes the cost, because instead of exploring configuration for a single connection, we can explore it on a network class basis. Second, it addresses the finding diversity, because similar connections tend to have similar optimal configuration. And third, it addressed high dimensionality because it provides us a basis for differentiating the performance model for diverse connections. While network classes address some of our concerns, we are still left with the core question of how we can find the optimal configuration. So Configanator takes an online approach with the key intuition that offline approaches are not realistic. It's not very realistic to represent the high dimensionality of internet in offline environments. So to search for configuration in an online manner, we have tons of options available. Like there's efficient exploration algorithms available, like Bayesian optimization, that use Gaussian process to build performance models and suggest next configuration to search. While these algorithms do provide efficient exploration, they have 2 major drawbacks. The first is that they are very sensitive to noise, which is a key part of our problem. And the second is that they have suboptimal exploration because they isolate the learning models for the different workloads, and in our case, different network classes. But intuitively, if we have data available for one network class, we can apply those patterns to another network to try to find a good or bad direction. And because of these two drawbacks, we observed that it results in up to 2 times lower median improvement compared to the optimal. On the other hand, we have machine learning techniques available like decision trees or random forests that are very good at exploiting patterns. But the key limitation is that they do not have any efficient exploration part. So one can use random exploration to generate some training data, but that incurs cost. So as the individual algorithm does not address our domain-specific need, the key idea behind our algorithm is to use the best of both worlds by designing a contextual multi-arm bandit. So this contextual multi-arm bandit has an exploration arm that uses Gaussian process and has an exploitation arm that uses machine learning based decision trees. To address the issues regarding noise, we also have a third resampling arm that re-evaluates all data points and consolidates the Gaussian process performance models. Now, the decision regarding the decision of context rests on this question that how much can we further gain by testing out a new configuration? So we use Gaussian process to calculate expected improvement, which is a standard metric, and it puts a probabilistic bound on the gain that we can get by exploring further. So intuitively, if this bound is high, it means that a good configuration is still out there and we should explore more. So looking at the high-level workflow of Configanator, it uses a split plane architecture where there is a centralized control plane called config manager, and there's config agent, which is a piece of code running at each edge server. So the web server works as it works today, gets requests, sends out responses, and the config agent in the background monitors the connection characteristic and performance and feeds this data to the centralized config manager. The config manager ingests this data to update its models and churn out new configuration decisions that are then pushed back to the config agent, thus completing the feedback loop. Zooming into the edge server, we developed a config API as an interface that config agent can use to interact with the connections. So since HTTP is an application layer protocol, we added callbacks to web server that config agent can use to tune connections at a very fine granularity. For TCP, we use a kernel module so that we can tune the socket option directly from the kernel itself. So moving on to the evaluation, our evaluation tackles a number of different dimensions. We compare against different algorithms to test out convergence. We evaluate performance improvement, fairness implications when we are reconfiguring the TCP and HTTP configurations. We evaluate system overheads and dissection of improvement and some deployability considerations. However, due to the time limitations, I will be mostly focusing on the performance improvement here. We have a pretty big paper. We have like 5 additional pages in appendix. So if you are interested in evaluation, please read the paper. So we took a 2-pronged approach towards evaluating our system. The first was a trace-driven evaluation where we built a simulator that can incorporate diverse traces and simulates the interaction of our system and page loads. The second was a live deployment where we built a prototype for the system and deployed it to Google Cloud. Our users were spread across 4 continents by using a platform called Speed Checker. We had around 3,200 users in total. So looking at the performance improvement for 2 of our most diverse traces, that is Mavi from Japan and Global CDN is a proprietary trace from POPs around the world. We see that at median, we have around 15 to 17% improvement in page load time. At tail, the improvement can be as high as 67%. And we observed that most of the improvements were from networks such as that have low bandwidth or high tail, high latency and loss rates. Similarly, for the highest improvement was observed for content-rich websites. As we are exploring configurations online, there's also bound to be some cases where a bad configuration might be tested. So there is definitely some parts where the page load time is degraded. And the figure here dissects that where this degradation arises from. So we see two key reasons. First is definitely exploration when we are exploring different configuration. And second is a stale network class problem, which arises when there is a drift between the system's view of network and the user's actual network itself. Looking at the live deployment result, we have the improvement is around on a similar order. So at median, we have around 14.6% improvement, which is around 760 milliseconds. At tail, the improvement is around 26%, which is around 3,800 milliseconds. So it's pretty large. So looking at some of the related work, since I'm running out of time, I'll quickly just go through it. There's tons of work in web optimization, self-tuning systems, and transport optimization. Our key difference is that we do not create a new protocol, but we create a system that can identify where a protocol works the best. Instead of tuning a single configuration like TCP congestion control or initial congestion window, we develop a system that uses our proprietary algorithm to tune cross-layer configuration. And the third is our algorithm tries to address the high dimensionality and dynamics of real internet users. So in conclusion, there's a push towards customizable protocols that can be customized to the operating needs, and Configurat takes a step toward building such a system. We build an algorithm that tries to address this diversity in a fine-grained manner. And additionally, in the future, as we are looking into more cross-layer protocols like QUIC, we have much broader configuration and flexibility available. For example, one can try to map packet loss to the network, to the website priorities itself. So if there's loss, one can decide whether you need to retransmit the packet or send out new data that might be at a higher priority. And finally, our work currently assumes that we only have control over the CDN edge end. But if we have control over switches and especially user devices, there's much more one can do regarding reconfiguring the networking stack. So thanks for listening to the talk, and I'm happy to take any questions.